It's my pleasure to welcome Leila Carvalho. I practiced not enough. From the Department of Geography at the University of California in Santa Barbara. She is a professor in meteorology and climate sciences. And her research interests focus on mountain meteorology, monsoon systems, mesoscale meteorology, and tropical, extratropical interactions. Leila studied atmospheric sciences at the University of Sao Paulo in Brazil and received her PhD in 1998. 98, sorry. 1998. And she spent a postdoc at the Institute for Computational Earth System Science at the University of California, and then became an assistant professor at the University of Sao Paulo, a position she held until 2009, when she moved then to UC Santa Barbara, where she's been ever since. So today's talk is about the Sundowner Wind Experiment-first intensive campaign, understanding downslope windstorms in the Santa Ynez Mountains, Santa Barbara, California. Please welcome Leila.
Thank you. Thanks for the introduction.
Turn your microphone on, please. Little switch on top. Yep, it's on. I think so.
I need glasses again. Sorry. Okay, now? All right. So I want to take the opportunity to talk about this problem that I think is very important, not scientifically, but also socially important, economically important. So I want to thank the presence of everybody, and I hope this is engaging enough, and you can ask questions anytime. I'm here to listen more than talking, I hope. So I want to also thank my collaborators, Charles, who is here, Gurjan, my postdoc, who's working, Caitlin, Zigner student, Craig Clements from San Jose State University have been helping with this particular project. I also want to thank the collaboration with the National Weather Service and also with the Santa Barbara Fire Department, important for this project. Okay, let's talk a little bit about Santa Barbara. Where is this region? Why it's so different, and what's different about this area? So here's Santa Barbara. You see California. Oops, here, and Santa Barbara. This is a zoom of this area. And this is the Santa Ynez Mountains. You can see it's not like a rock mountains. So the elevations are relatively low elevations. You have the highest peaks in these regions are 200 meters high, coming from, say, 500 this region and increasing. And you have here the Santa Ynez Valley, also very important. And behind these mountains, we have the San Rafael Mountains, which are higher elevation. Those are the Channel Islands. And this is the region here where most of the population live. We see about 200,000 people live in this area, in this coastal area. And this is why this became so important. What are Sundowner winds? Sundowner winds are these gusty winds that are observed downslope of the Santa Ynez Mountains. They are northerly winds, and they typically peak from late afternoon to throughout the evening and morning hours. That's why the name Sundowners, when the sun sets, is when these winds peak. And they can increase temperature and decrease relative humidity because of adiabatic compression. So they're considered the most important fire weather regime in the region. And they're also important for aviation. There is a small medium-sized airport in this region, so it's also another important concern for aviation. So, but sundowner winds have also been related to most of the recent major wildfires in Santa Barbara. All of them, all of the major wildfires were intensified or spread fast because of sundowner winds. Sundowners are not the only reason why wildfires happen. Of course, you have field topography, but they are an important component, very important, the most important component in this case. So you see the number of fires, and you can see the fires kind of, when you see the perimeter of the fires, you see them coming towards populated areas because of the downslope winds. Some of them, those are not related to sundowners. Thomas Fire, the most recent one last year, was considered the largest of fires in terms of historical fire until now. Now there is the Carr Fire became the largest in California, but Thomas Fire was the previous one, the largest in California, and it intensified because of sundowners. So this is just to give you an idea, another story, interesting. This is the frequency of days with sundowners according to the National Weather Service. Maybe this is not the complete definition of sundowners, but this was based on their own data sets, and they classified sundowners based on wind speed. So when we have northerly winds with a wind speed greater or equal to 30 miles per hour, or wind gusts greater or equal to 35 miles per hour. And then this is based on a single station. The station has the longest data set. And you can see, first of all, there is a seasonality in these events. So the spring is the season for sundowners. But also interesting, we see this trend showing that the recent years have been more frequent. We observe more of these events in recent years. Although they happen every season, right? So sundowners are multi-scale problem, right? In this regard, the synoptic conditions are relatively well known, I would say. Every time you have conditions for strong pressure gradients, this is a condition that would create northerly winds, then you would expect to see these cross-mountain winds. And situations can be multi-situations. This is the worst case scenario when you have a high-pressure system built up north of California, over the continent, and then because the air is very dry in these cases, make a dry air. We are seeing colors is sea level pressure, lines are showing 500 millibars geopotential height. But there are cases like when you have different configurations of high and low, but every time that a high-pressure system creates this strong pressure gradients, we end up getting sundowner winds. So this synoptic scale is important because these events can be predictable in the sense of they may happen or not up to 48 hours in advance. However, when we look into the mesoscale features, that's a different story, because these mountains, they have first of all a complex topography in this region, different elevations, canyons, passes, and even a distance from the ocean varies, and a relationship with the valley and the San Rafael Mountains. So everything together makes the predictability of these events on mesoscale very difficult. There is a handful of stations available in the area, and those are in blue, showing these stations. A little more dense towards the eastern part, which is good, but they are not in the right or the best location for us to monitor or evaluate the complete event from a mesoscale perspective. So we see that we lack of information to understand this events. Now, the Santa Barbara Airport is where the Santa Barbara Airport is. There is a wind profiler, a little far from the mountains, but they are operating almost
2 years.
For 2 years, yes, since 2016. So I want to show you, first of all, this is a, just to give you an idea of the wind rows climatology for this region. Why I'm showing this, just to show a little bit how different this can be from east to west. So these east-west differences are important, and also as you move away from the mountains or in the valley, you have a totally different climatology of this wind. So this is climatology from 12 to 15. This is a yearly climatology, and what we can see, the onshore winds affect mostly of the regions. The onshore winds in the valley, they have a different orientation. As expected, the coast is there. But and its differences are representing seasonality on these events. Now, if you look into between 0 to 3 time, PDT, we can see these stations now are showing a lot more the frequency of the northwesterly winds increase and in most stations. So some of these events are sundowners in a sense that they intensify their gusty winds. With that definition, they are gusty winds. They are cross-mountain gusty winds. Others are just representing the mountain breeze, right? Circulation that's expected in all these regions. So this is what we want to understand when we get them, when they are just part of the circulation in the region. Okay. So most of the mesoscale features we have studied in these regions, mesoscale mechanisms, are strongly studied with modeling results because we don't have data set enough to study this region. And we have done this previously with case studies in Cano et al. With 2 kilometer resolution. And now this is our ongoing research. We got a grant. We are studying these events based on modeling results. And I want to show you one of these preliminary or results that we showed in Cano et al., showing just a motivation, one important aspect. Those are results, of course, are based on a model, 2 kilometer resolution. And this is when the case, when there was a fire, it was a very important case because there was a fire and winds were stronger, gusts above 50 miles per hour, and there was a big destruction in the city. So the fire was more or less at this position, the ignition. And then you can see what is showing in this figure is relative humidity at 6 p.m. and winds. What I want to show with this figure is, first of all, this figure clearly shows the contrast of air mass. We can see, based on relative humidity, how different close in the coastal area. Also shows differences in wind direction. You have more of the northeasterly winds here, northwesterly winds, and northeasterly winds, northeasterly winds over here. So it kind of shows these differences. Large differences in decrease in wind speed in these areas, close to the coastal area, very different, and increasing in different regions. So that gives you an idea that topography, proximity of the ocean, influence of the valley, and the east-west regime seems to be important. So they are different. They are not occurring when you have sundowners, when you have these strong winds. They are not uniform across these mountains. The other thing we found with this 2 kilometer resolution simulations was some of the mechanisms we proposed that would be related to gravity waves and critical layers. This shows geopotential theta. and these vertical winds, okay? Oh, sorry, no, this is theta are the lines, meridional winds are colored here, and vertical winds are colored here, okay? And these lines are showing where the Richardson number is less than 0.25, okay? And this is a conditions where there is no sundowners. This was a case study, particular case study, very dry condition, and this was the Resuscita fire event study in this case. So what we found as possible mechanisms in accelerating, creating gusts in this particular study was the fact that when we get the reverse of the basic state, right? The winds were reversal of the winds. Could be one of the reasons why we end up, when we have strong gradients, why we end up getting this intensification of downslope winds. And then we also see, for instance, in case of Resuscita fire, we don't see the reverse of the winds, but we see the indication based on the model that self-critical layers are important. I forgot to mention, this is the region of interest. This is San Rafael Mountains, 2-kilometer resolution, very coarse. This is the valley. We poorly see the valley with this 2-kilometer resolution simulations. Now we are doing research with 1-kilometer resolution. That's 1-kilometer resolution. And this was for the Resuscita fire. What I'm showing here is those are meridional winds, okay? Now we are resolving a little bit better the Santa Ynez Mountains, the San Rafael Mountains. This is the islands, so this is the coastal area. Those are the islands. And then you are seeing this is mid-afternoon at 2 p.m. And then you can see that mixing layer, very clear here, forming some wave activity. And then strong winds are a little aloft. This is a cross-section where the ignition point was. So that we were interested in knowing what happened during this event. When, because in reality, what happened? We had the northerly winds throughout the day, but then these winds start picking up in the evening, and then the fire got completely out of control. In this case of the Resuscita fire, and it was a major problem, evacuation and property loss. That's why we are so interested in this particular event. And then we can see even in the simulation near the ignition point some indication that we had some onshore, shallow onshore winds, but the northerly winds were very strong aloft. But then, when it was after sunset, but basically it was not very after sunset. It was around 10, 11 p.m., and we were there. We saw this was actually very, very realistic. When we start seeing ashes all over the place, all over Santa Barbara, and then the firefighter said, all hell broke loose. This was in the news the next day. The fire got completely out of control during the night. And so what the model showed is, you see the jet, the nocturnal jet, the structure of the nocturnal jet, indication of wave break activity, maybe a rotor. If you consider this is an indication, is a 1-kilometer resolution, modeling results indicating that it might have happened during this day, why things got so out of control. And you can see in the valley, also calm winds, so this decoupled in the valley, very strong in the lee of the mountains, and then it moves away. So the wave activity is not very far towards the ocean. It's closer to the coastal area. That's another important thing about this region. And this was a good example because there was a very strong event in the region and documented in the sense of being a fire.
Where's,
Sorry.
Where's the ocean here?
The ocean is, okay, the land would be, the ocean would be here, where you see more the blues, probably.
So that's an island offshore?
This is an island. This is an island. This is one of the islands. We are just doing a cross-section. But you can see that even downwind of the islands, there is indication that there is some also activity on the lee of those islands. So we had this idea then to have more measurements, and we had the first Sundowner Wind Experiment. It was a small field campaign. I had a very low budget, $7,000, to do this campaign. So what we could do with that? Well, we could launch radiosondes with that. So that was the idea, launch weather balloons every 3 hours to try to understand, enhance our understanding of these profiles of winds, temperature, humidity, and other thermodynamic variables, evaluate the temporal variability of these profiles, identify the nocturnal low-level jet that we saw before, investigate mountain waves, if possible, and improve our understanding of sundowner mechanisms at the same time that we want to understand the forecast skill of the WRF, using WRF, okay? So we had this campaign was possible because my collaborator from CSU has this mobile profiling system in this truck. So he could drive the truck. So that's the most expensive part of the launching. Came with these two students, and then the team from Santa Barbara. We spent the day, the night doing this experiment. The logistic was also possible because of the Santa Barbara Fire Department let us use their space. So we had a very, the logistic was largely got benefit by the Santa Barbara Fire Department. And of course, the National Weather Service, who provided the forecasts for us. And all the time, we were on the phone all the time. They were helping us and getting data, sending data. It was a very interesting experiment. So we launched about 13 radiosondes from this location. This is where the Santa Barbara Fire headquarters is, Fire Department headquarters is. It's about 80 meters above sea level. This location is in the foothills of the mountains. And what were the synoptic conditions for this particular event was driven by this trough that was coming. So you have the trough. This is showing 500 millibar wind. So you have a jet nearby crossing the region, slightly north of us. But at low level, we have the low pressure system, but especially, do you see the pressure troughing in this area, kind of creating this strong pressure gradients that were detectable by the rule of thumb of the National Weather Service. They compare two stations, one in this region, more or less, and in Santa Barbara Airport, and they say, oh, the forecast is telling us may have pressure gradients greater than 3 millibars between these two, not gradients, they measure difference, pressure difference between -3 or lower, and then there's a chance you guys can get your Sundowners. So we went for this experiment based on this. It was a good forecast. And here is what happened, okay? I apologize for the lines. I'll try to explain a little bit. These are winds based on these stations that we have available. And I want to point something out. So this is nighttime is between these dashed lines. And what I'm showing here at the top are the stations that are in the valley, okay? There's 2 stations in the valley. You can see that calm winds throughout the day, mostly onshore. Afternoon, peaking in the afternoon, very calm in the evening, showing, okay, decoupled completely from whatever is happening in upper levels. Now, in the lee side of the mountains, coming from this direction, so I'm trying to put west towards east, in different elevations. So this is a little higher elevation, and you can see the intensification. Those are mean winds, right? This is in knots, 40 knots at some situations. As for sustained winds, we don't see a very wow, we're talking about the winds. You guys get winds here, much stronger sustained winds. But I'll show you what happened with a gust, also important. We see at the airport where the profiler is, which was not working this day for some mystical reason, wasn't working, so we don't have the data from the profiler. But we can see from the station that there was these two peaks in the winds, the northerly winds after sunset, weakening and intensifying again. And here show the gusts. When you look at the gusts, you can see, first of all, I want to point this out because this has been an observation that the National Weather Service has been talking about a lot, and we observe this as important too. You see that the onset of the northerly winds doesn't happen at the same time in all stations. First of all, those are gust winds. Now, those are more intense, and now you can see the importance of this event. Also, they don't end at the same time, right? So you have this east-west differences in the onset, intensification, and end of the event. We see that some station now, this is showing, this particular station here, is relatively high elevation, but is also showing the strong onshore or the influence of early in the day of the onshore winds, and then turning to north quite suddenly, turning to north and intensify overnight, right? This is very different from what you observe in the valley. So showing very different, very close, very different. This is actually a mountain winds, downslope mountain winds. Oh, this is the nighttime. Okay, this is for temperature. We don't see in this particular case a very strong effect on increasing temperature. We see for some stations like this increase in indicating adiabatic compression, the effect of the adiabatic compression. But for the stations westward, because the mountains are not so high, and this particular event wasn't so warm, you don't see much of this effect throughout the day. We see some peak when the winds were stronger, get stronger gusts. We actually see some fluctuations in temperature at low elevation. Now, those are the main results for the radiosondes. Okay, here we are doing is an interpolation. So every blue line is the time of the launching. Everything else is interpolated. I'm in dashed lines here. I'm putting more or less the elevation of the mountains, where nearby the highest elevation of the mountains is about 1,000 meters. And then here I'm showing wind intensity. Most of these winds, it changed direction. I'm not showing directions just to not make it too busy, but you have to believe me. So early in the day, we can see the onshore, the elevation, the influence of the onshore wind is shallow. So this is shallow marine layer penetrating the region, right? And then we can see the northerly winds kind of more intense aloft, kind of decoupled from this, very clear. But then as we move towards mid-afternoon, late afternoon, we start seeing this very interesting feature. Weak winds aloft, right? And very strong nocturnal jet forming at very low elevation. This is above ground level, okay? So you have to add 80 meters to this. So about ground level, you see, you were asking me about the elevation of the jet. So it's a very low elevation according to the radiosonde. And this is a very indication of mountain waves occurring. I'll show you more evidence later. Then after this happened we don't know exactly the timing of the nocturnal jet. We have 3 hours difference. This is an interpolation. But then our sonde of the 9 p.m. Indicated something completely different. So the weakening of this jet was clear. We were observing at the site. So we said, these winds are gone. And the weather service said, we think that this is it. I don't think this is going to intensify again. The National Weather Service said because they were looking at the pressure differences and they didn't see anything major. So later, the next launching, it was at 2 a.m. actually, 2 a.m. Then we start seeing this very strong intensification of the jet at very low elevation. If we were not looking with our own eyes, we would say, this is garbage, I would say. This is not happening. But because we were there, we saw the balloon going so fast, like so horizontally, very close to ground level. We were concerned that it would hit some obstacle, some tree or something, because it was really very strong. We could see and noticing, then we immediately look into the outputs and we realize, there is a jet. And it was a very shallow one. And now notice that you have more of these calm winds aloft and a very close to ground. So all these features are below the elevation of the mountains. So later on, we start getting the onshore flow. This is very also noticeable in this station data and also with the radiosonde. Any questions about this figure so far?
Where did you say the radiosonde station was located?
The radiosonde station was located, here.
Okay.
So that was...
What time is sunrise?
Sun rises at 6:10.
So on that figure, go back to that figure you just...
This?
So that the cessation of the jet, is that associated with sunrise?
This, no, it was before sunrise.
Before sunrise.
Before sunrise.
But when it ends, is that it's getting close to sunrise?
Yeah, this is a little of interpolation. I will show you later, but...
So it's a katabatic jet?
That's what we think it is. That's what we think is happening. I will show you other evidence that it might be the case, but okay. So here I'm plotting the same kind of plot, but including theta V, right? Potential temperature, virtual potential temperature, and showing along with winds. And I can see, okay, before sunset, we see the normal diurnal cycle, mixing layer, a little, forming early in the morning, midday, not early in the morning, we have the onshore flow, and then we have, at this point, we start seeing the mixing layer building up. But then, around mid-afternoon, we start seeing this feature in theta indicating, you see the drop of 300 theta, dropping down and up, and this was for us an indication of a mountain wave breaking, and this increases stability at this level close to sunset. So it's stationary. You can see it lasts a few hours, right? And increasing stability at very lower elevation, relatively lower elevations in this case. This is coincides with the sunset. Now you have the sunset, the cooling at the ground level is very fast because we are in a region very dry. This is a very dry area. So it cools, the radiative cooling is very fast. as soon as the sun sets behind these mountains at this time of the year, it sets behind the mountains. So about 6 p.m., the sun was already, there was already shades in some of this, most of the mountain areas. And then we see the jet intensifying. Now, when you see the secondary peak happens actually when you have colder air. In this, so you don't see this effect anymore, but you start seeing the increase in stability. We can see also in this map, this is the Brunt-Väisälä frequency being plotted, just consistent with what we are seeing there, right? And you start seeing this intensification in the stability, and then the jet forming. Now, why did the jet weakens? Here is what we think happened. Because once you have the jet, if you look now at the Richardson number, and you see very low Richardson number, indicating that you have turbulence, right? Turbulence, the stratified flow becomes more turbulent. And turbulence likely mix the air with low wind speed from surface and near surface level, mixing the air with the high wind speed. So that would possibly explain why the jet weakens. In addition to the fact that the wave activity seems to be less intense or not characterized at this point. However, cooling continues happening in the mountain slopes because this is nighttime. And then it could possibly explain the increase in this stability and then the re-intensification of the jet by this time, right? So this is consistent with the jet, just intensify. And then the end of the event when it's possibly not creating a cool, maybe too cold. I don't know why, how to exactly to explain the end of these events, but increased stability very close to ground level too could be another reason. Okay. No. Okay. Now, I want to give a few words about the forecast of this event. We used WRF to do the forecast. I'm not going to go in details regarding configuration of the model. It's a lot to discuss, but this was used first with an M, and then we did the 6 hours forecast. Charles and Gurjan did this part. And then we validated during this period of the experiment, and we did some preliminary sensitivity tests. So many sensitivity tests were done before, so we choose the best configuration. For this, I just want to show what we got in this regard. So what WRF does? Well, it's a 1 kilometer resolution. This is the forecast. We are using Planck-Shue ACM2 as a surface model. In this case, we see all kind of possibilities when you look into these comparisons. We see that if you are looking to the that station that had the strongest winds, well, WRF underestimated a strong wind. WRF did a better job for stations in the middle, between the east and west regime, but did a poor job close to the coastal area, indicating, well, the boundary layer, the marine layer is a problem for those models. To forecast will always be a problem. At some points, the model is more similar to what we observe for the gusts, but not always. But it gives a good idea of, this is going to be an event. And but the onset of the event wasn't so, at least compared to these Ross stations, were kind of not so well shown. However, if you now we did this comparison looking to observations, same, put a cross-section in the area where we launched the balloons. So this is observations, and this is WRF forecast. Keep in mind, this is 1 kilometer resolution, right? And this is an interpolation. What did WRF see? Did WRF see the jet? Yes, WRF predicted the jet in the evening, becoming intense, becoming more or less at the same elevation. This was an important result. Overestimate winds from the jet. It shows also this weak, the layer of weak winds aloft, kind of simulates well these onshore winds and the end of the event. It also put a secondary peak on the jet, which was extremely important. However, an hour late. We look into more than 1 hour resolution to see if the was exactly at this point, a little earlier, a little before. It doesn't change. It put a little late than what the model is showing here, what the radiosonde is showing here. But it shows these two events. And they are important because why the jets are important? Because they are related to gusts. In case there is a need of, or there's a fire, or there is we should look into this with confidence, and that's why we need to know better the jet, the behavior of the jet, and the predictability of the models. I also now want to show what WRF did at the time, these 2 times when the jet was the strongest, and then, but now we are looking at 10 meters winds, okay? Just to see how well the model forecasts, this is a forecast of the wind variability along the mountains and how close it might be of observations. That's why it's so important to look into all these places, all these stations. The color shows where the stations are. And then you can see, we can see at the peak of the event, you see most of the winds are strong throughout the mountains. We can actually see the differences in wind direction from west to east. The strongest winds over the west part. Maybe it didn't compare very well at this particular point, but doesn't mean it doesn't compare, it's not realistic in representing winds, because ROS stations are placed whatever the Forest Service thinks is important. So can be a canyon, can be, the model is not going to resolve these issues correctly in 1 kilometer resolution. When the model put again the secondary peak, we can see very, very interesting features in the San Rafael Mountains, but also the Santa Ynez Mountains. You see these differences, more northerly winds, and a kind of a void of winds at the center area. Very calm winds in the side, and large differences east-west when you see the secondary peak. We don't know how the jet behaviors across the mountains. When you do the cross-section, this is the afternoon afternoon time, and then this is the evening time. We see again indication of a mountain wave break, as we just put this cartoon other way around, so you are convinced that this is well-known kind of cartoon to explain mountain waves. But we can see that the model actually shows the jet very close, very intense, at the slopes of the mountains, indication of mountain wave breaking when we have the strongest jets. Okay, I want to show, this is an actual picture. This was taken from an aircraft when there was a fire. And then the fire was this side of the mountains. And then we clearly see this side of the mountain. So we see this is the laminar flow becoming turbulent on the other side of the mountains. It's very clear. This is actually a feature that happens, and then we can observe when you have smoke, right? Okay, so lessons learned from SWEX. Well, first of all, we can plan an IOP 48 hours, 24 hours in advance. This is a good thing about, based on their synoptic experience of the National Weather Service. We think that this east-west contrast that we saw are extremely important, extremely interesting, and they have to do a lot with, first of all, the mountain wave break. Those are important, but also the rate of cooling, how the boundary layer evolves throughout the night, right? And interactions with the San Rafael Mountains could be important too. So all this rate of relative cooling, the stability, and how the jet behaves seems to be an important issue that we would like to understand better. These issues are difficult to predict, and they are key during the fire season. So if we can improve or at least understand how well the model is doing, it would be a great thing for the region. Now, the benefits of having a comprehensive field campaign. That's why I want to discuss also, listen, maybe talk to some of you about a possibility of having this major, or I would say major, but comprehensive field campaign to investigate how the boundary layer structure and dynamics when we have these events against when we don't have these events. And then we want to understand more about mountain waves, how they happen, why, what is the breaking, where actually mountain waves break. This is an important aspect. We want to understand better the low-level jet, the wind gusts, and then we want to be able to understand these variations in the boundary layer structure so we can improve predictability of these events. We feel that maybe some of you have been saying, oh, what's new about this? Well, the novelty about this is that, first of all, we have this combination of the marine layer against the mountain, fighting against each other and producing very interesting contrasts. How important are these contrasts in developing even better clinic sort of vorticity, maybe things that we haven't looked into. I'm trying to look into now. Didn't have anything to present at the moment, but something I'm trying to understand better, because you see these contrasts east-west might be important in the onset of the events. Because you see the very cool, wet boundary layer to the west may be also creating some kind of baroclinic perturbation that might be increasing wind speeds and responsible for the onset of these events. This is more of what we just want to finish this, showing this plot. This was what we first thought about when having this experiment design. Maybe a little ambitious. We should cut a few of these things, in my view. Our main concern is in this area here, because this is where people live, essentially. This is we need to understand what's happening across the mountains all the way to the valley. That's why we are putting stations and also LiDAR, wind profilers, sonar in this area. Those are the stations we have currently that are in yellow. And then increase the sampling of stations at the crest level and different levels across the mountains. At least have one row of stations that could see this, and also located such that we could understand better this contrast between east and west. And with that, I thank you very much for your attention, and I hope get some questions. Thank you.
Thank you very much for this very interesting talk. Are there any questions?
Thanks. Very interesting talk. Bleer, 1995, has an interesting article about the Sundowner winds, and he mentioned a historical instance from June 17, 1859, where they had extreme temperatures up to 133 degrees measured, and it killed a lot of the animals. And I was wondering if your study and your framework offer any insights or maybe even the potential to try to simulate that event and how frequent it might be in the future.
It's an interesting question. We think that there was it became of an anecdote kind of story that we actually don't know, because it looks like the instruments were not precise or well located. But yes, there are events like we had a very recent one in the summer when in July, when temperatures were 95 degrees in the evening at midnight. We couldn't open the door. It was like an oven, the winds plus the high temperatures. But, the issue with temperature is important, but it's not simple, because temperature, you have the adiabatic effect, that's true, but you also have advection. In this particular case, and I think the story that he tells and other tells, was because there was already a heat wave. So that situation when it's already hot, and then you increase basically 10 Celsius degree at the side of the mountains, due to adiabatic compression, so you are increasing. But if you have a more cool kind of situation, then this ramp in temperature is not as important. We have seen this. Is it important? It is important. When there's a fire, everything is important. The fire creates its own weather as well, but we think that winds are the most important issue to categorize at this point. And if we end up having the experiment, we'd like to have the experiment during the springtime, because it's not, early summer, most of the spring, so we are not going exactly to see maybe these very strong events that happen with temperature only in summer.
Yes, a nice talk. I was curious about that time series of the sounding data, wind speed, and it looked like you had a mountain wave breaking one at the beginning of the event, and then at the end you had right there.
Oh, sorry.
On the left side, you can see you have wave breaking, and then you have a katabatic flow around 2900 Z, that low-level flow. Now, in the WRF simulation, you have wave breaking the whole time, and you never get a katabatic flow. So I'm wondering, two questions. Number one is, why doesn't WRF get the katabatic flow? And does the katabatic flow play a role in extending the wave breaking?
Those are interesting questions that we can't, I would be waving a lot of my hands as we don't have any proof that this is actually, except because we are in one point, and this is an interpolation. Let me put back, instead of looking at the winds, let's look at the altogether. Okay, what we see when you look at theta v, we see, yes, there's the cooling at this point. This is when the secondary jet occurs. But I don't know exactly.
So what I'm curious about is essentially that katabatic flow has modified the shape of the mountain. So now you have a new mountain shape, and that could cut off your wave breaking. Once you change the shape of the mountain, and if WRF doesn't get it, it doesn't cut it off. So these are just speculations as well. But
interesting. Yeah. Oh. Yeah, I haven't thought about it, but. But then, what would be the way to approach this?
I'm guessing that why doesn't WRF get the katabatic flow? I don't know. Maybe it's the resolution. Maybe you check and see if there's a cloud above. If there's no radiative cooling, it won't get it either. So there could be something in the boundary layer in the PBL scheme that's inhibiting it. Ask Jimmy Dudia.
Jimmy? Yes. That's
you could look for a katabatic flow in the vicinity. You're looking
So you're looking at one point for this time series for WRF, and maybe there's something that didn't get that far, or there's some indication of it, because at night with the cooling slope, you should get something. So you should check if it occurred somewhere, but maybe not that location.
You have a clear nocturnal katabatic flow. I mean, you can see it in the theta E, you can see it in the winds. It's a beautiful katabatic flow. So the question is, why doesn't WRF get it? And what role does it play in the whole Sundowner wind evolution?
And predictability, yeah, it's an important issue.
Can you talk a little bit more about why spring is chosen for like your time of study? Is it because the marine layer is present and there's enough of a temperature gradient that you have a high chance of these occurring, or is it something more than that?
No, it's more related to the synoptic systems that create where, as we have this transition from winter to summer, the high pressure system also moves over the Pacific. Mm-hmm. And then you have this in a position such that it favors more of this strong gradient. So it's more, has been explained through the synoptic conditions that are transitioning from winter to summer. So summer, the high pressure is closer to the continent, and it's transitioning during spring, and then could create more conditions for the peak of conditions favoring the cross-mountain winds. In other words, yeah.
Yeah, I was just going to mention that in this simulation we used the forecast from NAM. It was just one initial condition, so there might be some sensitivity to the initial condition. But that's a good point to investigate.
Any other questions? Nope. If not, then let's thank Leila again.
Thank you. Thank you for your attention and questions.